Coming back to the driver also has some amount of course. The inputs are such that different menu settings. For example, a lot of people don't like blind spot assist, or they don't like the LEDs. They find it a little annoying. So those people can also disable the feature into the menu by going into the menu settings. So those are the inputs which is given by the driver. And the inputs coming from the vehicle to the driver are, of course, the visual cluster warnings or the LED blinking. So that was how basically the blind spot algorithm works. And hopefully this has given an idea on how interfacing with the driver and the different components inside the vehicles. We can move to the next feature. So next feature I want to talk about is front collision avoidance system. Now, front collision avoidance is pretty self-explanatory. It is designed to avoid any kind of collision in front of the car. And this is not really a feature itself, it's a group of features. So there are multiple different features working at the same time to avoid the front collision. And let's see how those work. Okay. So first of all, the front collision system uses two types of sensor: the front long range radar and the front windshield camera. It uses the different, and again, there is a lot of use of sensor fusion where both the radar information and the camera information is extracted and uh, processed to determine target vehicle and how far the target vehicle is. And typically, the front collision avoidance system has three different features. First is the pre-collision warning, then comes the autonomous emergency braking, and third is evasive steering assist. Now, different vehicles or different OEMs have different production names for these features, and there is a good chance that not all the features are present in all vehicles because these vehicles are these features are expensive and they are currently only available in most of the higher trim vehicles. But the complete system typically has these three features. So let's see how the feature actually performs in a real life situation. So let's say the host vehicle is coming at a certain speed, and there is a target vehicle which is currently stationary. It can be stationary or it can be moving, but for the sake of example, we can say it is stationary. And what happens is the radar and the camera determine how far this target is, and based on the approach speed of the host vehicle, they calculate the distance to collision, total distance or the total time in how many seconds the is about to happen. And there will be three courses of action in this moment. The first will be a collision warning, that is similar to what you are seeing on this image. So the cluster send out a warning to the driver and tell that, hey, you are approaching too fast for this stationary target, so please slow down. And that will happen for a few meters, depending on the situation. Let's say the driver has failed to engage or has somehow ignored the warning. The second feature will come into action, and that is the AEB feature, also known as autonomous emergency braking. And that feature will start engaging the ABS system, the anti-lock brake system, and it will start to apply brakes or to the vehicle. And it will start to, and these braking actions are typically very aggressive, and there will be certainly a very aggressive deceleration. And usually, most of the drivers by this time they get alerted and they take control. But let's say the driver has still failed to take control of the vehicle after the deceleration, and the deceleration may or may not be enough to avoid the collision. So once it's at the more dangerous area of the collision, uh, the third feature comes into play, which is called collision mitigation or evasive steering assist. So this feature, what it will try to do is it will try to steer the vehicle away from the target. And there is no guarantee that the collision will be 100% avoided, but at least we can guarantee that the impact will be reduced because now the host vehicle speed has decelerated to a very great extent, and because of the steering action, there might be very little damage done to the vehicle. As I said before, not all the features are available together all the time, but more higher trim vehicles, typically the high trim Ford vehicles or Mercedes brand vehicles have all the three systems in place. And I've already mentioned the threat classification is typically done using the radar and the camera. So this is how the front collision avoidance system performs. Um, in the next slide, we will see the boundary diagram and understand. Let's look at the boundary diagram for front collision system. So front collision avoidance system, again, it's the typical structure of our boundary diagram. There are three components: driver, vehicle, and environment. Let's start with the environment. So environment is typically any target vehicle, any stationary objects on the road, could be like a barricade or some kind of a wall, or it could be even a pedestrian. So pedestrian detection is still not very common because pedestrians are very small objects and it's very hard to detect pedestrians, but I think some systems are still capable to do that in today's cars. And of course, there are lane lines and different types of road geometry in the environment. So, as I mentioned before, there are two sensors involved, the front main radar and the front windshield camera. So, the front main radar and the camera both will try to detect any kind of target object in front of the vehicle. Once they are detected, they will be again transmitted to the sensor fusion algorithm. So, as I said before, both the sensors are typically seeing the same object. But the reason we have multiple sensors is because not all sensors are perfect. The camera, sometimes the camera is more effective, sometimes the radar is more effective. For example, the radar doesn't work pretty well if there is a lot of fog or there is a lot of snow or some kind of physical object blocking the radar. And the camera doesn't work pretty well when there is rain or glare or some kind of an dirt which is blocking the camera. So both the sensor inputs are given into the sensor fusion algorithm, and the sensor fusion algorithm processes it and determines the targets and what kind of targets they are, the size of the targets, and again the uh, information then goes into the target tracking and selection algorithm. Target tracking selection algorithm will use inputs from the vehicle model, for example, vehicle speed, the steering wheel angle, and other different types of inputs. And using all those information, it will determine the threat level of a target. And once that target is determined, it will go into the front collision logic. And as I said, there could be multiple features inside the front collision, and it will all the different features will act at different times. So the uh, first line of action will be the PCA or pre-collision warning. The pre-collision warning, once it determines that the car is about to hit a target, it will send out the cluster warning and the audio chime and try to warn the driver. And once, let's say, the driver has avoided that and there is need for a braking action, then the AEB logic will act into place and it will start giving the inputs to the brake controls module and the brakes will be applied. And and let's say in this model, I haven't included the steering action, but if there was a steering action, there would be another logic of steering assist, and that will be given to the steering control module. So the reason I did not include steering logic is The evasive steering assist is a very high-end feature, and it's not, and that is because for any kind of steering action, we require a power steering control module, and these are typically very expensive and only available in many high. Most majority of the production vehicles only have AEB and PCA. And of course, from the HMI point of view, there is the cluster warnings which are going directly to the driver in the form of audio or visual, or in the form of the deceleration also. And the driver also has a freedom to change the menu settings. Some of the features have different sensitivity level. Let's say if the driver feels that the system is too sensitive to target vehicles, then you can go and change the settings for the menu and accordingly adjust the feature according to your convenience. But this is overall how the front collision avoidance system works, and it's a very great feature. It has saved millions of lives over the course of time, and this is also one of the features which Euro NCAP has mandated on all model year 22 vehicles. So I think that's a very good news, because this is a very important feature to avoid any kind of collision fatality. So those are the uh, active safety features I wanted to discuss. And next, I wanted to talk about a little more interesting feature, that is a convenience feature. That's the adaptive cruise control. So adaptive cruise control is typically my favorite feature. The reason being, I am an active user of this feature, and I also work in this on this feature in my day-to-day job. Adaptive cruise control, I think I mentioned this before, but let me go over, is a level 2 feature. Remember, level 2 means partial automation. That means this feature is able to take over only certain driving actions from the driver. And what this feature does is, the driver can set a desired set speed, let's say 25 miles per hour, 50 kilometers per hour. And the driver can also set a gap setting. A gap setting means, so this is how the buttons usually look like. So driver can set a gap setting. Gap setting is how far from the lead vehicle are you comfortable to be. So it will maintain the amount of distance you set in this gap setting button, and it's going to maintain that gap throughout the driving condition. And what this feature really does is, the driver sets the set speed, and the radar and the camera, again, they help in tracking the target vehicles. And if they feel that the target vehicle is too close, or it's breaching the gap setting distance, in that case, the car will automatically slow down. And once the target vehicle is far enough and out of the range, the car will again re-accelerate and bring you back to the desired set. So it's a very interesting feature, and it's a very good feature to reduce driver fatality, especially for drivers who drive 4 to 5 hours. The vehicles, the ACC system uses typically the front radar and the front camera. This feature has been there around for almost 10 years now. And when in its initial iterations, it was only using radar as the main sensor. But since then, the computer vision technology has really improved, and now we also use the camera. So the camera is able to do many other activities, such as since the camera can visualize on what the type of vehicle is in front, they can camera is able to determine the size of the vehicle and the type of the vehicle. So it's a really interesting feature. So adaptive cruise control is a closed loop feature, and what that means is uh, there is so it's not just a warning feature like the pre-collision or blind spot detection system. So the feature is able to detect a target, and it's also able to act upon it. So the way it acts is, involves the powertrain control module and the brake control module, and of course the ADAS control module in a closed loop system. And all the driver has to worry about is steering the vehicle. And this vehicle is still level 2, which means it is not. This does not mean that the driver can completely relax and take their foot out of the accelerator pedal. They still need to be ready to take control because the sensors are not perfect and the detection algorithms are not perfect. So, but this feature works pretty well in most cases. And over the years, this feature has evolved into many different types of additional functionalities. Typically, one of the examples is intelligent speed assist. That means, let's say the camera is able to detect the speed limit of the road, and the feature is automatically able to adjust your set speed according to the speed limit. So these are some of the interesting modifications which have happened over the years. Let's look at the adaptive cruise control boundary diagram. Adaptive cruise control boundary diagram, again, we have over 3 areas: the driver, vehicle, and the environment. From the environment, there are two things. First is the target vehicle, which is the vehicle in front, and the lane lines, because the lane lines help the camera to determine whether or not your car is in the line of collision. So the environment is then detected by two sensors: the front windshield camera and the front radar. It goes through the same process, goes to the sensor fusion and tracking, and then it goes into the goes into the arbitration logic. And what does arbitration logic mean? So arbitration means it categorizes different targets into different categories. So there are two logics here. First is the distance control, the gap setting which the driver has maintained. Let's say the driver has decided to have a gap setting of 10 meters from the front car. This arbitration logic makes sure that the host vehicle is always maintaining that 10-meter gap. And it uses, of course, different types of inputs from the vehicle CAN and, of course, the steering button output. And based on this arbitration logic, there is a torque request logic. Torque request logic has two primary tasks. First is to control powertrain, and second is to control the brake control module or ABS module. So depending on how fast the vehicle has to decelerate, the torque request is given to the powertrain control module, and the torque request, and let's say that torque request is not enough for braking. So then there is a separate request which goes to the ABS or the brake controls module. And this is the mode manager. Mode manager is basically taking all the information from vehicle CAN and it's taking all the information from the driver's settings. As I mentioned, the driver is responsible to set the desired set speed. Let's say the driver sets 40 kilometers per hour as the set speed and sets a gap setting of 10 meters. So all that information is given from the switch, all the steering switches, and it is given to the mode manager, and the mode manager then uh, arbitrates or conveys that information to the other logics. HMI point of view, there are two things. First is a cluster warning, of course. When there is a target vehicle in front, there will be some kind of graphic showing on your cluster to let the driver know that, hey, this car is now about to slow down, so this is the reason why we are slowing down. And then there is, of course, the steering inputs like the buttons. So that was adaptive cruise control, and it's a very common level 2 feature. Um, so the next feature we can go is the driver alert system. Again, driver alert system or driver state monitoring system, it's a very interesting feature again. So what this feature really does is It determines if the driver is paying attention to the road all the time. And the traditional system which we have for the past few years is just a lane keep system. Basically, what happens is it uses the front windshield camera and it determines the lane lines of the road. And let's say the driver is crossing the lane lines very frequently, then the system recognizes that the driver is maybe distracted or maybe tired or drowsy. And if that is detected, then a warning is given to the driver that driver alert and please take rest or take a break. So that used to be the old system, and it was effective, but not also so effective because lane lines, just crossing over lane lines, is not a very good feedback to determine if a driver is alert or not. There can be other reasons also for the driver to not be alert, which is why in today's technology we have a new sensor set, which is the driver state monitoring camera. And this is currently present in the Audi system and the Tesla autopilot system, also in the Ford autopilot system. So what does this does is there is a front camera on top of the steering wheel, which is constantly monitoring the driver's face and using facial recognition. And it determines and it looks at the driver's eyes and the direction in which the driver is looking. And let's say the driver is looking at a phone or looking at somewhere else other than the road, uh, and the driver consistently does that for a certain amount of time, then the cluster will give out a warning, something like pay attention to the road or something like that. So this is a very useful feature, and it's rolling because of the driver state monitor camera. It's becoming very useful in the coming years. And as I mentioned before, we are slowly in the phase of transferring from level 2 to level 3 automation. And in level 3 systems, these will be particularly very useful because even though the car is capable of doing all the driving in level 3 system, but the driver is still responsible to pay attention. And this driver state monitoring camera is the kind of like a system, which policing system, which is making sure that the driver is still attentive in the car and not letting the car do all tasks. So the driver alert system is a pretty simple system, as I said. It typically involves the environment is basically the lane markers and the road attributes. The front vision system or the front windshield camera looks at the lane lines and tries to determine whether the car is within the limits of the lane lines. So that information goes into a sensor signal processing and sensing model. This is typically the camera vision, computer vision detection, and that information goes into the lane keep system logic. So lane keep system is another different feature which we'll briefly touch upon. Lane keep system is responsible to detect the lane lines and maintain the car within the bounds of the lane lines, and that's why both the systems use a similar. So the signal processing model goes to the lane keep system, and then all that information goes to another algorithm called the impairment or distraction monitor. So what this does is it keeps a statistical count of how many times the driver has been distracted from the start of the vehicle, and there is a certain threshold. Once that threshold is crossed, like let's say the driver has crossed the lane lines 20 times in a given distance, and based on that statistical approach, the distraction is determined on how distracted the driver is. The system is currently also taking the input from the driver state camera. As I said, the driver monitoring camera will give the distraction rate on like where the driver is looking and the driver is currently not paying attention. So all that information is collected and it goes to the warning manager. This warning manager is responsible to send out the CAN output. Uh, So warning manager determines what type of warning should we give to the driver. Let's say the driver is crossing the lane lines very frequently, then there will be something like take rest or pay attention, something like that. There will be a warning. If the driver is not looking at the road or is looking somewhere other than the road, then the warning message will be different. So the warning manager determines what kind of warning to be sent out to the driver. And the mode manager, of course, consists of all the settings which the driver has selected. So in some cars, the driver can also add custom messages on the warning. They can add a visual warning or an audio warning. So they can customize that. So all that information is stored in the mode manager. And then there's the CAN output. The CAN output is the cluster warning or cluster chime. So I think I've covered most of the boundary diagram. So yeah, that is how, and then the driver also interacts. The driver input is, of course, the driver state monitoring camera, where whether or not the driver is also the lane behavior of the driver, on how well the driver is following the lanes. So those are the different inputs from the driver to the vehicle system. So in future, we will have more modifications. Some of the ideas are, let's say the driver is distracted, then the navigation system can also search the nearest rest area or a coffee shop, and it can automatically send that information on the navigation route. So these are some of the future modifications which can happen on this system with more robust connectivity and more robust internet system. We can have that kind of capability.